Okay, can't leave the previous topic alone quite yet. Let's just make what's hopefully some brief observations. So if we have, let's say a V versus U. Now before I had U versus V, excuse me, V versus U is probably more traditional. We saw that if I have a rectangular region, that can give us just about any kind of a path. The path around a rectangular region here is going to be a path around something. Could be an ellipse in the XY plane, something more complicated, even something pretty weird, as we found in the last set of examples. In general, if we have a region of the UV plane, then it's bounded by one or more curves that correspond to hopefully a simple curve in the XY plane. If this curve can be described simply, then since a typical region here will become bounded by a couple of vectors over here giving us a parallelogram, etc. If we have some function f of xy over here, and that function is to be integrated over this region, then what do? Well, f of xy, presumably x equals some function, I'll call it alpha of uv, y equals beta of uv. Then we can express f of xy in terms of u and v as f of alpha of uv beta of uv. Just as the area of the region in the xy plane is double integral of RU cross RV du dv, where the integral is the UV over the UV region, and R is xi plus yj, where x stands for this function of uv and y is another function of uv. The integral of f of xy with respect to y and x, integral over our xy region, and I don't want to bother putting a lot of notation around these regions. In the first place, R is a good thing to use for region. We've already used R here. There are all kinds of reasons I don't want to do that. I'm just going to say that the integral of f of xy dy dx over whatever region this is, bounded by whatever hopefully simple curve this is equal to the integral of just f of xy times the magnitude of RU cross RV du dv, where this integral is over the presumably simpler UV region that corresponds to the XY region. And it's pretty easy if we just think of how a typical region here relates to a typical region here. Our integral of f of xy with respect to y and x is just represented on this small region, or approximated in the small region, by f evaluated at xi star and yi star, where xi star and yi star are representative points in this region that correspond to ui star, vj star, representative point within this corresponding region. Whatever our values of u and v here, they determine our value f of xy here. Whatever our delta u by delta v is here determines what our two vectors are here, our ru and rv, ru du and rv dv vectors. So that multiplying the value of f evaluated at whatever x and y correspond to this sample point here gives us the value of f at the xy point, sample point, corresponding sample point in this region, multiplied by the this quantity is the multiple of the area, that is this quantity times the area of this region is the area of this region. So if we multiply our value of f at this point by the area of this region, which is the du dv, multiplied by the multiplier, the ratio of areas, we get the value of f at this point multiplied by the area of this region, which is what we use to set up the integral in the xy region. Just to be as clear as possible, this would then equal, we could express this as the integral of f of alpha of uv, beta of uv, times the magnitude of ru cross rv du dv over the same region. And just by way of summary, this little box is delta u by delta v. These vectors with this as our r vector is our ru delta u and rv delta v, and these derivatives, this is a vector, these partial derivatives are vectors, and this region has area, magnitude of rv delta v cross ru delta u equals magnitude of rv cross ru delta u delta v. And I'm not sure I've kept that all on the screen. This region contributes to the integral of f of xy f of xi star yi star times the area being this, giving us this integral, and xi star is your alpha function evaluated at ui star vj star, yi star equals our beta function evaluated at ui star vj star, where ui star vj star is our sample point in v versus u plane. it doesn't take much for our transformation functions, transformations from u, v to x, y, and back, to get quite complicated, difficult to determine whether they're invertible, difficult to determine whether a given curve here gives us a simple curve, or even a closed curve here will generally give us a closed curve here. But whether that curve is simple or whether that curve crosses itself, whether that curve comes around and runs along itself for a ways and then comes back, all kinds of things can happen, but those things are beyond the scope of what we can talk about in a basic vector calculus course, but hopefully that'll pique some interest, and in some cases of people who are have the time and inclination to do really well with this stuff might want to consider some more advanced courses.